So I hope I've convinced you that when you have excess acetyl CoA, excess fuel in general, you are going to be synthesizing fatty acids for storage. So last video we had sort of went through and highlighted sort of how we differentially regulate degradative versus synthetic processes. We're going to have a whole lecture that we will devote to how we actually really do this regulation. But we have a significant compartmentalization of processes where beta oxidation of fatty acids occurs in mitochondria. And it's really important that we do not have that acetyl CoA that's derived catabolically from the breakdown of fatty acids somehow be a signal that we have excess acetyl CoA, that we're in a fed state. And we do not want this catabolically derived acetyl CoA from lipids to be going back out into the cytosol and being just remade into fatty acids. So it's really important that we highlight that this excess acetyl CoA is really excess acetyl CoA that comes from carbohydrates. So that's what we're just going to kind of walk through here. We're going to remind ourselves of the transport systems that are sort of involved in this process. So excess fuel, specifically we're referring to carbohydrates as excess fuel, because if we've got lipids as excess fuel and they're already as fatty acids or triglycerides even, they can just get immediately stored. We don't need to make them into triglycerides. So we're not going to take excess fats, break them down to acetyl CoA, and then resynthesize them back into fatty acids and triglycerides. So this is really carbohydrate derived. So we're going to have glycolysis, again, that occurring in the cytosol, and then pyruvate dehydrogenase chemistry, that's going to be in the mitochondrion. Pyruvate dehydrogenase chemistry is in the mitochondrion. So now we're going to have acetyl CoA, okay, that is going to be excess, but that is going to be in the mitochondrion. Okay, so here's what we need to do. The net that we want to happen is we want to be able to get acetyl CoA out into the cytosol. So we want acetyl CoA in the cytosol. But as I hope I've highlighted, there is no acetyl CoA transporter. Okay, we do not have an acetyl CoA transporter, so we cannot take and just transport acetyl CoA from the mitochondrion out to the cytosol. That's an important sort of safety check, right? Because we want to make sure that we don't just have acetyl CoA anytime it's in excess kind of going out there, because catabolically derived acetyl CoA from fatty acid breakdown could get out there. So here's what we're going to do. Excess acetyl CoA in the mitochondrion, generally derived from from carbohydrate metabolism, is going to dip briefly into citric acid cycle chemistry. We are going to have citrate synthase sort of doing chemistry here. So I'm going to highlight where these are on the picture that we have over on the right here. So citrate synthase is right here. Okay, so here's sort of where we're starting. So this is going to be starting here. I can't spell start here when we have excess acetyl CoA. So excess acetyl CoA in the mitochondrion from pyruvate dehydrogenase chemistry, taking glycolytically derived pyruvate, doing chemistry with it to generate acetyl CoA. Citrate synthase is going to convert it into citrate, but that is in the mitochondrion. So here's the key. We have a transporter to get citrate out into the cytosol. So this is a big key here, that we have got a citrate transporter. So we have got a citrate transporter there. It's called the tricarboxylate transport system, but it's a citrate transporter that allows us to get citrate out into the cytosol. Now, maybe you remember, and if you're a research student, I know you do, that we have mitochondrial and cytosolic isoforms of malate dehydrogenase, but there is only mitochondrial versions of citrate synthase. So we don't have a cytosolic version of citrate synthase for us to sort of reverse this chemistry, but what we do have is an enzyme called citrate lyase. So here is citrate lyase, okay? So here is citrate lyase. So citrate lyase is going to go back and make oxaloacetate in the cytosol plus that acetyl-CoA in the cytosol. So the net is we get that acetyl-CoA out because we combine it with oxaloacetate, kind of disguise it, if you will, as citrate. Citrate gets exported out. We uncouple that oxaloacetate from it, and now that acetyl-CoA can live in the cytosol and it's ready to do its fatty acid synthesis chemistry. Now, one of the things that we're going to highlight here is we're going to take that oxaloacetate and it's going to go back into the mitochondrion. Okay? And it's going to use the malate aspartate shuttle for that. And if you don't remember sort of what that is, that's the conversion of oxaloacetate into malate using NAD plus and NADH, sort of with redox chemistry, and we ultimately get oxaloacetate back into the mitochondrion. And why this is really important here is I just wanted to highlight that normally we would be talking about using oxaloacetate in the cytosol if we are going to be doing gluconeogenesis. We are in a fed state right now. We are not going to be doing gluconeogenesis. So this is not for gluconeogenesis because we are in a fed state. If we have excess carbohydrates that we are breaking down to make acetyl-CoA, we are certainly not going to be doing chemistry to have gluconeogenesis be revved up. Okay, so hopefully that tied in with some of the content that we talked about on this last slide. Again, if you haven't seen this video, make sure to watch that one maybe first. But this one kind of walks through sort of those transport issues and how we get that catabolically derived acetyl-CoA, largely from carbohydrates, that is then going to be used and assimilated into fatty acids that we can then store as triglycerides.